All right. More often than not, when people think of geometry, this is the kind of stuff they think about: areas and perimeters, working with shapes. They don't necessarily think of the logic that you need in order to figure out various things about these geometric shapes. So the proofs and the rules and the theorems kind of get lost in the mix. So what we're going to take a look at today are called composite figures. They're usually made up of more than one shape, simple three-dimensional figures. I was going to say, you guys have played video games, haven't you? Maybe once or twice? Possibly. You ever seen some of those older games where the three-dimensional figures look awfully blocky or not real good? See, one of the things that they use is they use triangles to go and make up the surface. And the more triangles that they can compute and calculate for on the figure, the nicer and the better the graphics look. But that takes an awful lot of computing horsepower to go through and do that. So that's why a lot of the older games were like that, because the computing power just simply wasn't there. So by going through and doing that, making those kinds of shapes, they can make nice looking graphics, right? Didn't think I could tie that into something you guys played with. I know. There, I what? Okay, now Minecraft is designed to be that way. Okay, but they also have an extremely high resolution on their blocks. Okay. So it's give and take on there, but that's part of what it is. And when you take a look at the features on the images that they put on there, they do it, it's done in a certain way so that it's high resolution, extremely quick frame rate of refreshing, but you can actually use it on very limited computers with limited computing power. So if I want to find the perimeter of that composite figure, that's just simple, isn't it? Because don't you just simply take, whoops, sorry. Why don't you just take 5 plus 3 plus 4 plus 7 plus 4 and add those up? Let's see, so we get 10, 8, 18, 23. 23 feet. Easy enough, right? So I'm going to give you a moment here and make sure that you get this taken in to your little books. You put it into your books. Okay. As you look at this, this might seem awfully obvious. If two polygons are incongruent, they should have the same area. Does that mean if they have the same area, they're congruent? You sure about that? Stake your life on it? You'd stake your life on it that if two objects have the same area, that they are the same shape. And you would be wise not to. Why? Well, here's a little taste of it. What happens if I were to draw a triangle like this, right triangle, and I said that this base here was 2 and that was 3? Could I also draw a triangle that looks like this, that says the base is 3, but the height here is 2? Would that also give me the exact same area? Yeah. So, got to be careful about that. Just because the area is the same does not mean that the polygon or the shape is going to be exactly the same. I mean, after all, could I have a square that has the same area as a triangle? So, keep that in mind. Area addition postulate is just makes sense because you have the areas, you add them together, and you've got it. So, if I want to find the area of this figure, I notice here that this and this and this and this, these are marked so that they're congruent. Does that mean the triangle on the left is the same as the triangle on the right? Well, if I consider that if I have 8.5 here, would this be 8.5 as well? So in that case, I've got side, side, side that the triangles are congruent. So I know that all I would have to do is find the area of the rectangle. So for the rectangle, that's going to be 6 times 8.5. And, oh, come on, don't be temperamental. Calculator was right there. So I got 6 times 8.5, and I end up with 51 for that one. Now for the triangles, the base, would I use 8.5 as the base? Would that work? Multiplied by the height of 4 divided by 2, correct? 4 goes in, or 2 goes into 4 2 times, so that means that I would end up with 17. So that would be 17 plus 51 plus 17. Does that work? Okay, so that means that I end up with 85. We're in inches, so that would be inches squared. It's always nice when you have a drawing on there. That way you're able to go through and figure out what's what. So, how about this one? Now here I had added them. What operation would I have to do to figure things out here? Subtract. Because it looks like a triangle is taken out of a rectangle, correct? So it looks as though I would have 26 multiplied by 15. So I could take 26 multiplied by 15, and I said multiply. And I end up with 390. Then I would have the triangle, which would be 22 multiplied by 12 divided by 2, correct? So really that's 11 times 1, or times 12, which would be 132, correct? Okay. So if I add those together, does that mean I would end up with, we get a 2, we get a 2, and we get a 5? Oh, I'm supposed to what with them? Okay. So granted, I'm writing notes out here and I'm doing things. Always write it out so you know what you are to do, because it'll kind of put it into your brain. Oh yeah, I'm supposed to subtract. So I got 390 minus 132. So that means I have 258 millimeters squared. There's the area of the shaded region. This is why work is important to write down. That way you know which operations you're doing, what your numbers are. So I got this. Diagram shows the plan for a reflecting pool that will form part of a new downtown plaza. The edge of the pool needs to be tiled. What is the perimeter of the pool that will need tiling? So, question for you. Is this side here the same as the side that should be right there? Could I, so you're saying that this thing here, I couldn't take this side and push it out till I got over to here? That wouldn't work? It wouldn't stay the same length? Well, I'm not worried about the corners, because I could take this side here and push it up there. Okay. But let's think about it this way. They got 25 yards here. They didn't go and state it over here, did they? It's kind of hard to draw it in there. So they said, hey, if it's 25 here, does this have to be 25 there? If this is 40 up here, does this have to be 40 down here? So does that mean the distance from here to here is going to be 50 and 25, 75? Would it also be the same distance over here? Would it? Okay. How far is it from here to here? 100. How far is it from here to here? Oh, so this is pretty easy to deal with, isn't it? Even though it is a weird looking shape, it doesn't bounce out and come back in again. Everything is nice straight lines. You could push it all out and make a rectangle. Okay. I mean, there's no piece that goes and sticks up on one side or goes in too far that we'd have to account for. So really, we just got 75 plus 75 plus 100 plus 100. So we end up with a grand total of 350. If I learn how to spell, this helps. 350 yards. Okay, that's it. That's easy enough, isn't it? How about this? What area will I need? Would it be easier to do the subtraction like we did on the last one, figure out the area of the whole thing, and then take off the pieces? Or would it be simpler to say, break this up, you know, maybe draw a line across over here. So I got a rectangle here, which I know would be 25 by 60. And then, well, I suppose I could break it down this way. So I got a rectangle, rectangle, and rectangle. Or would that take more work to figure that out? Yeah, it would be more work. I mean, since the figure, we know what its dimensions are on the big side, which is going to be 75 times 100, right? So that would be 7500. We know that we've got 40 times 25, and 40 times 25 is going to be what? 1,000, right? So if this is 1,000, would this one up here also be 1,000? So I could subtract off 2,000, correct? So that would be 5,500 yards squared. There you go. But again, draw it out, write it out, see what you come up with. So with those thoughts in mind, what I want you to do is give practice problem A a try and see what you can come up with. Okay, here we go. Did you draw out the figure? Okay, so a composite figure is made up of a rectangle and triangle that has 3-inch horizontal side. Okay, so horizontal means that it's going this way, so I know that I got this way is 3. Okay, 2 vertical sides, 4.5. So could I have them coming down this way and this way? 4.5, 4.5. And it says I have 2 4-inch sloping sides. Could I do that this way? That would be 4 and that would be 4. So could I draw it out like that? Is that the only way I could have drawn it out? No, I could have put the on top, couldn't I? But since we're looking for the perimeter, we've drawn out something. And again, the numbers don't have to match the actual size. They just have to match the picture that we've got. So all I got to do is add these up for perimeter, right? 4 and 4 is 8, 9 and 3, 17. I get 20 inches. Am I right? Good. Good start to the day, right? So I'm going to give you a couple of minutes here, and I want you to do practice problem B. So see how you did. I'm supposed to determine the area of the figure. Well, what do I have? I appear to have a square After all, it's got the mark here, it's got the mark there, and it's got the mark there, so that means it's 4 and 4, right? So for the square, that's going to be 4 times 4, which is 16. Now, I am also supposed to take care of the other shape, which is a semicircle, half of a circle. So, which is going to be pi. Now, they wanted us to keep it in terms of pi, so we are just going to use the pi symbol. Do not use 3.14. So it'd be pi times the radius. Well, if this is 4, what's the radius? 2 times 2 squared. Then I got to cut it in half, right? Which is 2. Well, what's 2 squared? 4. So, that's 4. 2 goes into 4 2 times. So this works out to be just 2 pi. And how do I express the area of this thing in terms of pi? 16 plus 2 pi centimeters squared. That's it. That's what it will look like. Okay? So the numbers that you can calculate out, you calculate. Instead of putting 3.4 into a calculator, you just keep the pi symbol there, just like an X or a Y or whatever variable you want. And then you can write it out with this. Okay. So I'm going to give you another couple of minutes here, and I want you to do part C. Alrighty. So I'm going to get rid of a few things over here. Now it says that a rectangle with dimensions of 3 by 1.5 centimeters is moved from the bottom left-hand corner. So that might look something like that. Would you agree? So that's going to be 3, and that's 1.5. Now, it wants us to express our answer in terms of pi. Well, this is something that we can go through and calculate out. Okay, so that would just simply be 3 times 1.5, which would be 4.5. Would you agree with that? Now that's got to get subtracted from something. What am I going to subtract it from? 16. So if I take 4.5 from 16, I end up with 11.5 plus 2 pi centimeters squared. Where did I get what from? Okay, this was what we had found from part A. This was the original of all of it. Okay. Yeah, just a continuation of it, yeah. Okay, there we go. Alrighty. I'm going to give you a couple minutes, and I want you to work on problem B. Alrighty. So it says a new office building has one side in the shape of a right triangle on top of a rectangle. So they tell us how things should look. So we've got a rectangle and we've got a right triangle. Okay. Does that work? Like I said, your pictures don't have to be perfect. They just have to be a representation of what's going on. Now it says the rectangle is 420 feet tall. So that's 420. And 120 feet wide, 120. The triangle's base is 120, so we know that it's sitting on there the right way, and its vertical leg is 160. So, what is the perimeter? Well, I know that it's going to be 160, 420, 120, another 420 over here. What's it going to be here? That I don't know. Because it's a right triangle, what would I use to go and figure that out? Pythagorean theorem. So that means that it would be 120 squared plus 160 squared is that. And so that means I got 200. So that squared is 200, so we got 200 down there. So that means 200 plus 420 plus 120 plus 420 plus 160. 1,320. Did we get that? Did you get another one right? Ah, yeah, well, that's still not too bad, just using your head. So there you go. All righty. So I'm going to give you a few moments here, and I want you to do part E. So, area. Well, that should be fairly easy. Can I do the area of the rectangle and the rectangle and the area of the triangle by themselves and add them together? Yes. Well, isn't that what you'd want to do? Because I know how to go and figure out the area of a rectangle on there. That's pretty easy. That's just going to be 420 times 120, correct? Then the area of the triangle, well, that would end up being 120 times 160 divided by 2 plus 50400. So that means I would need how much glass to cover that? I would need, yep, 60,000 feet squared of glass. Okay, there you go. Assignment is due at the end of the hour on Monday.